This presentation will go through the process of building a predictive flood model based on data from Calgary, Canada. My name is Saya Sheth, and this is my midterm presentation for land use and environmental modeling. Flooding is the most common natural disaster in the US and across the globe, amounting to billions of dollars in damages from economic and agricultural losses, damage to ruined infrastructure and property, and public health risks such as increased injury and even mortality. To mitigate the impacts of flooding, which will only increase with climate change, municipalities and planners can implement predictive flood models to help them prepare for flood events and thereby reduce damages and decrease risk to citizens that will ultimately increase community resilience through early response mechanisms. This is a preventative approach, which differs from other flood approaches, such as building large infrastructure projects or implementing policies around climate change after flood events have happened. The goal is to develop a model that accurately predicts which areas in Calgary are at high risk of flooding during a flood event, and to test the model on a similar city to understand the model's generalizability. The model uses the shown significant features. First, a fishnet grid was applied to Calgary. Then, these features were engineered in ArcGIS Pro using a digital elevation model, hydrology shapefiles, and land cover open data. In Arc Pro, maximum flow accumulation, mean elevation, maximum slope, majority land cover, and distance at 25 meters to the nearest water body were engineered using geoprocessing tools. These features were then joined to the fishnet using the zonal statistics as table tool. The model is a logistic regression, with the outcome being the probability a grid cell will become inundated with water during a flooding event. The most significant features out of the ones chosen are maximum slope and mean elevation, which have the lowest p-values. The results of the model's predicted probabilities are shown here at a 20% threshold, which was chosen arbitrarily. To improve the model, threshold iterations can be calculated to get a threshold that predicts the most true positives or predicts the least false negatives. This is a decision municipalities and planners can make before implementing a model. This model predicts better if a grid cell is predicted not to flood, compared to grid cells that are predicted to flood. This is still useful, as a high accuracy for predicting areas that won't flood can inform municipalities of safer areas during flooding events. Next, the model needs to be validated using goodness of fit metrics. The sensitivity suggests the model does not predict that well when it's predicting flooding. However, the specificity suggests the model predicts very well when it's predicting a grid cell that will not flood. The accuracy is high for these two prediction rates. Next, we look at the ROC curve, which has an area under the curve of 0.7869, indicating it's a relatively good fit since it falls between 0.5 and 1. The final goodness of fit metric for model validation is cross-validation over 100 folds. The chart shows the average accuracy across the 100 folds, which is concentrated around the mean, indicating good generalizability of the model to different cities. These maps show the final predictions for Calgary based on the model, along with the confusion metrics for those predictions. Next, we run the model on a similar city to understand its generalizability. Denver was chosen as a similar city based on relative size, mountains, climate, and urban life. The exact same process was completed for feature engineering. The model was run and is visualized here. While the model does not work as well as anticipated on Denver, the predicted areas of flooding slightly align with the city's stream network. To make a more robust and generalizable model, other features such as soil and intersections of hydrological features could be added. Additionally, new thresholds should be applied to get more true positives or more false negatives, or less false negatives. The model should be tested with more features and across more cities before it is implemented by planners and municipalities to predict flooding. Thank you.